So here we're going to consider the normal distribution. The normal distribution, or the bell-shaped distribution, or the Gaussian curve, or the mound-shaped curve, looks somewhat like that. Has several features to it. Let's talk about the features, and let's talk about what it's representing. Along this line, along here, is what is going to be known as the random variable. So the random variable is the thing that we're measuring. So if I'm measuring the amount of water, for example, I consume in a day, it could be anywhere from 0 at this end up to maybe, I don't know, 5 liters in a day, somewhere between those 2 points. And I can have any amount of water that I want between 0 and say 5 liters. You say, why don't you have more than 6 liters? Well, I could have more than 6 liters. I've just chosen a value to put on there. So this is the random variable. The amount of water I have is it's random and it's variable. It's more than one possible outcome, and I don't know what the outcome is really going to be before I actually do it. So it's random variable, the thing that we're interested in. It may well be normally distributed, which basically means that the center point is going to be where most of the occurrences occur, or most of the water consumption occurs right in here. So let's just say, for argument's sake, that the average is 3 liters per day. So if my water consumption is normally distributed with an average of 3, it means that most of the time the mode is going to be 3, the median is also going to be 3, and the average is also going to be 3. This is some of the characteristics of the normal distribution. It's symmetrical down the middle. There's a line of symmetry down there. There's a mirror reflection of itself this way and this way. And the area under the curve corresponds to probabilities. So if I wanted to work out the probability that I have between 3 and 4 liters of water a day, I'd have to measure the area in here. And we're going to see how you do that. Excel is going to be of big use to us. Since the area under the curve corresponds to probabilities, so long as we put all the possible outcomes on this curve, and we will actually, because theoretically this curve stretches out to infinity in both directions, the area under the curve will be 1 or 100%. So if I include all possibilities, then the area under the curve, which corresponds to probabilities, is 1 or 100%. So that's, again, like me saying that if I have an exam next week and you guys take it, I can say I'm 100% certain of what your grade's going to be. And I could say that's because it's going to be, say, for example, an A, B, C, D, or an F. Because they're the only outcomes, so I'm obviously 100% certain because I've included all possible outcomes. The curve is just called asymptotic, and a just means not, and symptotic are Greek words to mean not, to fall together. So ptosis is the word mean to fall, sim is together, and a is not. So asymptotic basically means it doesn't fall together, and that's in reference to the tail, the end bits, which are known as the tails. I'll just magnify that a bit. So this comes down like this, and this line just continues to go out, and they don't actually touch at any point. They get closer and closer, but they never fall together, asymptotic. So this is these are the basics of the curve. Where the curve is lower, like here, my consumption is going to be lower. My consumption is going to be lower over here. Many things in the real world occur according to the normal distribution. Let's take an example of how it works. So let's imagine we've got 3 guys, and they're going to go out for a drink. And this is the random variable is how much they drink. So that's going to be our random variable. And they may have, I don't know, 0 liters of drink or they can have 1, or they can have 2, or 3. It's just a number line, and this is the random variable, what's under observation. We don't know before they go out what they're going to drink. It's variable, it's not a fixed number, and it's random. We don't know what it's going to be. So there you go, 7, 8, 9, 10, and so on. So let's just assume that we've got 3 guys that are going to go out for a drink. And so Mr. Green, let's suppose Mr. Green has an average of 3 pints, and that's a standard deviation spread of 1 pint, and that his drinking habits are normally distributed. Well, if they're normally distributed, I know that the mean will be at the center of a bell-shaped curve. So I'll try and do this as best I can. So the curve is going to be a certain height. Now, according to the empirical rule, we know that if we add and subtract 3 standard deviations, you get 99.7, approximately 100% of the observations. It's not quite 100%, because the curve keeps on going to infinity that way and that way. But most of the observations, or most of the times this guy goes out and has a drink, will be between plus or minus 3 standard deviations of the mean. So 3 standard deviations of the mean, it's going to be 1 standard deviation, 2 standard deviations, 3 standard deviations, and the other way 1, 2, 3. So it's a normal distribution curve. 99.7% of the observations are between these 2 points here and here, and it's going to max out there. So maybe do it like this. Okay, so that's Mr. Green. Likewise, Mr. Red, when he goes out, he has an average of 4 pints. And the standard deviation is equal to 2. And let's suppose his drinking habits are also normally distributed. So it's going to be centered at 4. And there's going to be 3 standard deviations. This guy's standard deviations are 2. So it's going to be 1 standard deviation, 2 standard deviations, 3 standard deviations, and then 1 standard deviation, 2 standard deviations, 3 standard deviations. You may say, well, that's a bit weird. How can it be going to negative numbers? The normal distribution is a theoretical distribution. So you can get things like that occurring. So it's going to be centered at 4. Now, the area under the curve must be equal to 1. So what that's saying is that this curve's got to be wider for sure, but because the areas under the curve must be 1, it cannot be as high as this one, otherwise the area would be far too wide. So it's going to be lower. It's going to be spread out. So it's going to be centered there. It's going to go off like that, and it's going to go off in this direction, something like that. And let's take Mr. Blue, and let's say Mr. Blue, when he goes out for a drink, he drinks an average of 5 pints, and his standard deviation is going to be also 1 pint, and his drinking habits are also normally distributed. So these guys all have normally distributed drinking habits. So this guy is going to be centered at 5. The standard deviation is going to be 1, so most of the observations are going to be between 3 standard deviations of the mean. 1, 2, 3. And it's actually the blue curve is just going to be the same as the green curve, except it's shifted along, because the spread is exactly the same. But the only difference is that the mean is 5 and it's not 3 like the green curve. So it's going to be the same height as the green curve, and it's going to be something like that and that. It's supposed to be the same. It may look a little bit higher, but it's supposed to be the same. So even though we've got 3 different guys and they all have normally distributed drinking habits, their curves don't look exactly the same. When the mean changes, like between the green and the blue curve, the curve shifts along the line. And when the standard deviation changes, when it becomes larger, the curve is more spread out and flatter. So it's not enough just to say someone's drinking habits are normally distributed. You have to give additional measures, some side measures, and those side measures are called, in Greek, parameters. Parameters, para just means side, and parameters and metas means measures. So it just means side measures. And the side measures that you need to totally define where your normal distribution sits in space are the mean and the standard deviation, assuming we have population data, that is. So the side measures I need to totally define the specific normal distribution curve for you are the mean and standard deviation. I need those side measures to be able to do that. So supposing now I want to figure out the probability that these guys drink between 3 and 4 pints. So between 3 and 4, that's what I want to find out, that they drink between 3 and 4 pints. For Mr. Green, the probability that they have between 3 and 4 pints is the area under the curve between 3 and 4. So this is the area, or the probability, corresponding to Mr. Green having between 3 and 4 pints. Mr. Red, the probability that they have between 3 and 4 pints is the area under the red curve between 3 and 4. And for Mr. Blue, the probability that he has between 3 and 4 pints is the area under the blue curve between 3 and 4. And you can see that these areas are all different. So even though all three guys have normally distributed drinking habits, because their parameters, because the side measures, because the mean and standard deviation are different, the probabilities, or the area under the curve, is different for each of them. So when this theory was developed a long time ago, maybe 300 years ago, they knew that the formulas to actually work out the areas under the curve were horrendous. So it was decided by Gauss, who was developing this theory at the time, that he was going to actually come up with a book or a manual. And in that manual, I can look up the probability. For example, just look up, there's lots of numbers. There'd be a little graph telling you what exactly the book was working out for you. It's working that area there, for example. And it would tell you, it would have values in there. So the area between 2 points, whatever it was, the area less than a certain point, it can calculate it for you. But what the guy developing it, Gauss, realized that he had an issue, because just in this simple case, he's got 3 different guys, and trying to work out the probability they have between 3 and 4 pints would be different for each of these guys. So he would need a different page for each of these guys to work out their probabilities, because the means and standard deviations are different. He realized that there's an infinite amount of mean and standard deviations that are available and possible out there. I may be looking at something other than drinking. Example, I may be looking at the students graduating at the age of graduation, and it may be that the average age is, say, 23, and the standard deviation may be 5 years. So if I wanted to work out probabilities, assuming this is normally distributed, I may want to work out probabilities for this, scenario I've set up here. And the only issue with this is that I'm going to need to get another table, another page. So Gauss said, well, we're not going to do that. That's just going to be too much work. So he decided, the guy that developed the theory, he decided he's going to come up with a special case. And this is the special case he came up with. He said, I'm going to write a table, a book, for a very special case of normal distribution. And let me just do it over here. That special case is this one. And it's a special case. He's going to call this Z right here. And he's going to give it a special name. It's going to be called the standard normal. I'll draw it in a moment, but it's the standard normal. When we see the Z, we know we're dealing with that special case, standard normal, for which Gauss actually came up with one table for the standard normal distribution. Anything you want to work out for the standard normal distribution, you can. So So this is the standard normal distribution. And what's special about it is that the mean is equal to 0. It's centered at 0, and the standard deviation or the spread is at 1. So if I go 1, 2, 3, and -1, -2, -3, I'm going to get most of the observations in that range. And he came up with a table for this, just for this. He didn't come up with a table for these guys, but he came up with a table for this special case. And it's like, how would that be useful to us? So, well, this is how it's useful to us. Obviously, he was a smart guy. Let me draw the standard normal distribution on here. It will be centered at 0. The mean is 0. And the standard deviation is equal to 1. So it's going to be centered here. Standard deviation is 1, so it's going to be 1, 1, 2, 3 standard deviations. I get nearly all the observations, like that. And then it's going to be -1, -2, -3. So -1, -2, -3. Don't be put off by the negative signs. And so then we're going to get it going off like this. And he has a table for this. Anything you want to calculate for this curve, any probability, any area under the curve, you can calculate using the manual that Gauss came up with, which is right here. So how's that useful to us? Well, Gauss realized for the green curve, the green guy is centered at 3. The average drinking habits are centered at 3. And has a spread of, as we said, 1, 2, 3, 1, 2, 3. Hold it, it looks just like the black curve. So it's got the same height, it's got the same width, but it's in the wrong place. So if I can just shift this curve along by 3 spaces that way, in fact, I want to take every value, like I want to take, say this 3, if I want to shift it 3 spaces that way, all I have to do is take the 3, call the 3x, and subtract 3 from it. That will shift the curve 3 spaces this way. So the 3, 1, 2, 3 will be centered at 0. The 2, 1, 2, 3 will go to -1. It's just going to shift the curve along. And now, once he's shifted it along or transformed it, he can actually use the table. How about the blue curve? Let's look at the blue curve. Can we do the same thing? The blue curve is centered at 5, and it's got the same standard deviation or spread, so it's got the same width. So all we need to do to get it to become the black curve is shift it by 5 spaces. So I take every value for the black curve, like 5, and subtract 5. It just shifts it along that way. So it's going to be x minus 5. And we're done for that. How about the red curve? The red curve is a little bit of a curveball. The red curve is centered at 4. That's what we said, it's centered at 4. And standard deviation is 2, so 3 standard deviations, and 1, 2, 3 standard deviations. So the first thing I want to do is shift it so it's centered at 0. So when I shift it so it's centered at 0 for the red curve, I'm just going to take every value and subtract 4 from it. Now that's going to shift this curve 4 spaces this way. So it's going to be now centered at 0. The only problem is that when I move the curve to 0, it's going to look somewhat, like this. So it's going to look like the same curve as the first one, but shifted along. Which is great because it's centered at 0 when we shifted it along. However, it's too low. So it's too spread out. So I need to reduce the spread. I need to reduce the standard deviation. And the way I do that is by dividing out this value by the standard deviation. I need to get the spread equal to 1. If the spread is equal to 2, all I have to do is divide by the spread. So if I divide by 2, it's going to have the impact of actually squashing this curve up to be that. So basically, let me go back and readjust this formula. X minus 1 divided by the standard deviation is 1, so it doesn't make a difference to it. And for the second one, the blue one, which had the same standard deviation, 1 again, I can divide by 1. Divide by 1 doesn't make a difference. So it's getting a bit busy there. So the general rule to take any curve and shift it back to the special case of the standard normal, I take every x value, and if you notice, for each of these, I actually subtracted the mean. The green mean was 3, the blue mean was 5, the red mean was 4. So I subtract the mean, and then I divide out by the standard deviation. I put it in as the population standard deviation this time. And that's the process. So Gauss figured out you could take any normal distribution, transform it using this, and it's going to give you the special case of the standard normal, which I can use this one single solitary table that he came up with to solve everything.